Let us check convergence and divergence of the following series. The summation of 1 divided by n to power 1 plus 1 over n. N starts from 1, goes to infinity. So which test help us the best here? If you break this guy down, 1 divided by n to power 1 plus 1 over n, you can write this guy as 1 divided by n to power 1 times n to power 1 over n. Or you end up with 1 over n times 1 over the nth root of n. So what I'm going to do, I'm going to use the limit comparison test here. Limit comparison test. The limit comparison test says, well, if you have two series, the summation of an and the summation of bn, and when you find the limit of an over bn as n goes to infinity, if this guy is equal to a finite positive number, then the convergence and divergence of these two series are the same. Convergence, divergence of these two series are the same. Okay, what I'm going to use the harmonic series here for comparison. So let us take this guy as your an, and for bn, I'm going to use 1 over n. I'm using the harmonic series which is a divergent series. Why is that? Why you're doing this? Because of the nth root of n. Because the limit of the nth root of n as n goes to infinity is equal to 1. That's the reason. So take a look. I broke an down into 1 over n times 1 over the nth root of n. And because of that, since I know the limit of 1 divided by nth root of n is equal to 1, I end up with 1 over n. So to compare this series, I'm going to use the harmonic series 1 over n. So let us take a limit using the limit comparison test. The limit of an divided by bn as n goes to infinity. Let me use the same color that you see up there. Which is equal to the limit of, well, an is 1 divided by n times the nth root of n, and bn is 1 over n as n goes to infinity. This can be written as the limit of n times 1 divided by n times the nth root of n multiplied by 1 down here. Or you could just cancel out n and n right away. No one's stopping you. I'm just showing you all the steps, all the algebra. Later, when you want to watch these and you want to see all details, they are there for you. When n goes to infinity, you can cancel out n and n. You end up with the limit of 1 divided by the nth root of n as n goes to infinity, which is equal to 1. But let's go back to limit comparison test. Since you have a finite positive number, It means that the convergence and divergence of these two series are the same. By the limit comparison test, since the limit of an divided by bn as n goes to infinity is equal to 1, which is a finite positive number, so the convergence and or slash divergence of series an and series bn are the same. Since we know that the summation of 1 over n as a harmonic series is a divergent series, so as the summation of bn, which is 1 divided by n to power 1 plus 1 over n, and start from 1, goes to infinity. For those of you who are curious that why the limit of the nth root of n as n goes to infinity is equal to 1, let me quickly go back to elementary calculus and show you how to deal with these types of series. To find this series, to find this limit, we write the limit of the x root of x as x goes to infinity. Now let y be equals to the x root of x. It means that y is equal to x to power 1 over x. Take ln of both sides. Ln of y is equal to ln of x to power 1 over x. As x goes to infinity. So here you have ln of y equals to, remember the properties of ln of u to power n can be written as, this n can be written in front of ln of u. So this guy is equal to 1 over x times ln of x as x goes to infinity. But if you use direct substitution, what do you get? You get 1 over infinity, which is 0, times ln of infinity, which is infinity, indeterminate form. So our goal is to rewrite 1 over x times ln of x as ln of x divided by x. So when x goes to infinity, to get infinity over infinity. Now you can apply L'Hopital's. So ln of y is equal to ln of x. Let me move it a little bit here. Ln of x divided by x, and we are taking the limit as x goes to infinity, which is infinity over infinity. So ln of y is equal to taking the derivative of ln of x, which is 1 over x, divided by the derivative of x, which is 1, then taking the limit as x goes to infinity, you get 1 over infinity is equal to 0. So what happens is that ln of y is equal to 0, it means that y is equal to e to power 0 or 1. So the limit of the nth root of n as n goes to infinity is equal to 1. Or the limit of the nth root of n as n goes to infinity is equal to 1. So we use this to find the limit of the general term using limit comparison test. Let us recap what we did. This is our series that we see here. We have 1 divided by n to power 1 plus 1 over n. This is your an, which can be broken down into 1 over n times the nth root of n. So I decided to use limit comparison test. Why is that? Because I know the limit of the nth root of n is equal to 1. So when I broke it down, I end up with a harmonic series to compare it with. Limit of an divided by bn as n goes to infinity. If this guy is equal to finite positive number, the convergence and divergence of these two series is the same. I'm using the harmonic series. Again, why is that? Because I know the limit of the nth root of n as n goes to infinity is equal to 1. So I can easily get rid of the limit here. So the limit of an divided by bn is the limit of 1 divided by the nth root of n as n goes to infinity, which is equal to 1. By the method of limit comparison test, since the limit of an divided by bn as n goes to infinity is a finite positive number, so the convergence and divergence of these two series are the same. But one of the series is basically the harmonic series, which is divergent all the time. So the second series must be divergent as well. And a quick recap for you, how to find the limit of the nth root of n as n goes to infinity. This is equal to 1. One of the techniques that we are using is, this is a popular method in textbooks, taking the ln of both sides without using any shortcut, showing all the steps here, applying L'Hopital's rule, and then, as you can see, the limit is equal to 0, but this is ln of y equal to 0. It means that y is equal to e to power 0 or 1. So the limit of the nth root of n as n goes to infinity is equal to 1.